Hello and welcome to the third video in the binary number series by MathsBytes. In this video, we will be introducing the decimal number system. We will discuss what decimal numbers are and the definition of the decimal number system, with making sure we are all clear about all the different concepts involved in the definition. I will then show you examples from the decimal number system and show you a very useful table, the place value table, and how to use it. Decimal numbers are the numbers you are using in your everyday life and were first taught in school. Examples of a decimal number are 478, 2005, and 698,751. We call them decimal numbers as deci means 10, and we use 10 digits 0, 1, 2, all the way to 9 in this number system. As I mentioned a minute ago, I would like us to discuss the definition of the decimal number system, but as I will be using definitions quite often in my videos, I would like to start by making sure everyone knows what a definition is. According to the Cambridge English Dictionary, definition is a statement that explains the meaning of a word or phrase. So armed with this knowledge, here is the definition of the decimal number system. The decimal number system is a base 10 positional number system. There are two important concepts in this definition, base 10 and positional. Let us discuss them in turns. First, we will focus on what positional means. Positional means that each digit in a decimal number have different positional or place values associated with them. This is very clearly communicated in the way we read out decimal numbers. Let us go back to the example numbers we looked at earlier in this video and use them to demonstrate this concept. When you are reading out the numbers 478, 2005, and 698,751, you are automatically associating the individual digits with their positional or place values. For example, in 478, you say 400, meaning that the 4 has the place value of 100. 70 means that the 7 has the place value of tens, and 8 only has single values, which is the place value of 1 or units. Positional also indicates that if you place the same digit into different positions, the overall value of the number will be different. For example, 847 uses the same digits as 478, but as we mixed up the digits, we now have 8 hundreds, 4 tens, and 7 units or ones. Now let us look at the example of 698,751. When you read this number out, you put the 1000 after the group of 698, which is also separated by a comma that groups the digits and makes it easier to read the number. This grouping means that each of those values are now 1000 times bigger. Therefore, the 6 is in the place value of 100,000, the 9 is in the place value of 10,000, and the 8 is in the place value of 1,000. Let us summarize this in a neat table. 698,751. This table is called the decimal place value table, and it will come very handy in the next few videos when we will discuss the properties of the decimal number system and when we will start talking about the binary numbers. When you look at the numbers in the table that represent the place values, you might spot that every one of them are multiples of 10. And not just any multiples. If you start from the rightmost corner and move along the table towards the left, you can create the new column by multiplying the previous one by 10. This discovery nicely leads us to the second part in the decimal number system definition. Base 10 has two parts to its meaning. First, base 10 means each place value in the number system is represented by an exponent with base 10. So our table can be modified to reflect this as follows. I hope you still remember what base means when it comes to indices or exponents, and what, for example, 2 to the 4 means. However, if you are unsure, I suggest you watch the previous video in the series on indices. Base 10 also means that there are 10 digits used in the number system. These are 0, 1, 2, all the way to 9. Remember, 0 is also part of the system, so 0 is the 10th digit. This nicely ties together with the name decimal that we discussed earlier when we established that deci means 10. Now that you hopefully have some understanding of the decimal number system, let us look at some more examples of decimal numbers and see how we can use the place value table to identify the values each digit is associated with. Let us try to place the following numbers into the place value table. In the number 567, the largest place value is for the digit 5 and it is 100. So we can place 5 under the 100 or 10 squared column. The next digit is 6, which represents 60 in the number, so it will go into the 10 or 10 to the first column. And the last digit is 7, that is in the 1s or 10 to the 0 column. This column sometimes also called the unit. The next number is 2022. This number has 3 2 digits and 1 0 digit. The highest place value is the thousands or 10 cubed, so we can place the first 2 in there. The next digit in our number is the 0, and it is at the hundreds or 10 squared place value. What it basically means is that this number doesn't have any hundreds. Remember, 0 means nothing in mathematics. This 0 also called a placeholder, and it has a very important role. If we left the placeholder 0 out from the number, we would have a very different number. Then we have the same digit 2 in the following 2 place values. So we can put a 2 under the 10 or 10 to the first and under the 1 or 10 to the 0 places. The last example is 4,458,789. The highest place value is the million or 10 to the 6th, and we have the digit 4 at this place value. The next place value is 100,000 or 10 to the 5, and it is also a 4. Then it is the 10,000s or 10 to the 4 place value with the digit 5. Next is the digit 8 at the place value of 1000 or 10 cubed. The following digit is 7 at the place value of 100 or 10 squared. Next is the digit 8 again, but this time it sits at the place value of 10 or 10 to the first. And finally, the last digit is 9 at the unit or 10 to the 0 place value. Before we move on to the place value questions, I would like us to spend some time on writing down mathematical expressions showing you the above numbers. This will come very useful when we will convert binary numbers to decimal numbers. So using the digit and the place values, we can also write the above numbers in the following format. 567 equals 5 times 10 squared plus 6 times 10 to the first plus 7 times 10 to the 0, which is also equals to 5 times 100 plus 6 times a 10 plus 7 times a 1. 2022 is equals 2 times 10 cubed plus 0 times 10 squared plus 2 times 10 to the first plus 2 times 10 to the 0, which is also 2 times 1,000 plus 0 times 100 plus 2 times a 10 plus 2 times a 1. And the last one, 4,458,789 is equal to 4 times 10 to the 6th plus 4 times 10 to the 5 plus 5 times 10 to the 4 plus 8 times 10 to the cubed plus 7 times 10 squared plus 8 times 10 to the 1 plus 9 times 10 to the 0, or equivalently 4 times 1 million plus 4 times 100,000 plus 5 times 10,000 plus 8 times 1,000 plus 7 times 100 plus 8 times 10 plus 9 times 1. And surprisingly, if you add up the sums, you get back the original number. Now you might ask, why go to all this trouble to write out these numbers in this unusual format? Well, this way we can draw the attention to the place values associated with each digit quite easily without the place value table. Also, when we will look at other base numbers, such as binary and hexadecimal, using this detailed sum of digits and place values will help us greatly to convert between the different systems. I hope you have a good grasp of the decimal number system and the decimal place value table now. So let us check your understanding with the following practice questions. Try to place the numbers into the place value table correctly, then write out the long sum of digit and place value combinations using both the index and ordinary notation. Again, feel free to pause the video here and spend as much time on the exercise as you need. We all learn at a different pace. Here are the answers. I hope you got them right, but if not, look at my answers and see why you might have gone wrong. Remember, mistakes are learning opportunities. You can uncover misunderstanding with making mistakes, so you won't make those same mistakes in your exam. Let us now go over what we covered in this video. We have reminded ourselves what decimal numbers are, then we defined what the decimal number system is, and we discussed in detail what this definition means. We also introduced a handy table, the decimal place value table, which we'll rely on heavily when we start learning about the binary numbers. We also talked about how to write out the digit and place value sums for decimal numbers. This way of writing out a number from the place value table will be very useful when we will look into converting different base numbers to decimal. Before we can start with the binary numbers, I would like us to spend one more video with the decimal number system and find out about the important properties of the decimal number system so we can compare and contrast it with the binary number system, and hopefully understanding the binary number system will become somewhat easier. Hope to see you next time. Until then, keep learning one byte at a time.